Okay, so let's go ahead and move on. We're going to talk about improving R performance now. Make sure I'm mic'd. Yeah, okay. So we're going to talk about improving R performance. First, we're going to talk about benchmarking. This really fit with the previous section, but just for the interest of time and keeping that nice 45-15 kind of thing going, this just had to get moved over. It's very quick, but it's very important. And like every exercise after the first couple in the first section uses this stuff. So benchmarking. A lot goes on when you execute an R function. A whole lot goes on. And here I just rattle off some examples. Symbol lookup, creating the abstract syntax tree, AST, creating promises, forcing them, argument checking, creating environments to evaluate things in. All kinds of crazy stuff happens when you execute an R function. So things like DLL lookups. A lot of these things are like one time only maybe. And so if you really want to get a sense for, I've created one method of doing something. Is it really any faster than somebody else's method of doing the same thing? A simple single system.time comparison between the two may not tell the full story. So I say this requires some care. There's a package, our benchmark. It's a simple package. It just does exactly what it needs to do, basically. How does it work? So again, we're just going to create some random matrix. Right? So the examples are fairly abstract, but they sort of need to be. We're going to revisit this T of x times x cross prod x business. Right? So I've defined the first one as function f, the second as function g. Right? So when I say g of x, this x right here, so if I say f of x, it's going to evaluate tx times x. G at x is going to evaluate cross product of x. Okay? Now, we load packages in R with library, so library R benchmark. And now I just say benchmark, f at x, g at x, and then I'm going to specify some columns that I want to see. If you just ran it without the columns, it would just basically give more information that would make it print a little less nice for display purposes here. And what does it do? By default, it'll run each one of these 100 times. And it will count the total time of execution. So F took 13 seconds total across 100 evaluations. And then G took roughly 4 total seconds across 100 evaluations. It'll also tell you the relative performance. So here, if G is 1, then F took 3.5 times longer to run than G did, even though they're doing the same thing. So fairly self-explanatory, I think, but very, very powerful, very nice. There's also micro benchmark. It has a different philosophy. I tend to use R benchmark. Micro benchmark does a lot of stuff that this doesn't, but a lot of the stuff that it does, I'm maybe not interested in sometimes. But it's nice too. I don't want to give the wrong impression. So we do the exact same setup: x, f, g. Now micro benchmark. We're going to load that, and we're going to run micro benchmark f at x, g at x, and I say unit equals s. So I'm going to benchmark in seconds. Micro benchmark because by default it'll actually be microseconds, and you can time in microseconds with it. I find that's usually not that useful. I think if you're worried about microsecond level performance in R, you're using the wrong language. But here we're just going to basically recreate roughly the micro benchmark version of what R benchmark was doing here. And it gives you a whole lot more stuff: the minimum execution, mean, median, quartiles, and then we can plot. So if we look at this bench object, output of micro benchmark, I can box plot it, and it'll give us this nice little plot. So that's kind of nice, right? So we can see there's really a lot of variability over here, but it's kind of nice. I don't know. So in summary, don't just do one evaluation of these functions. You should, if you're comparing multiple methods, don't just time single executions. You may give yourself or others the wrong impression about how things are going. This isn't like micro benchmark is a little more complicated. R benchmark you could basically write yourself, but why bother? Somebody's already done the work for you, right? So it's pretty nice. They already exist. They work very well. They're highly tested and used by many. I recommend them very highly. Okay. Questions about benchmarking before we move on? Okay. So now we're going to talk about free improvements. What do I mean by free improvements? I mean, you know, you maybe make one change once, and then forever you're getting performance boosts somehow. Basically, I'm naming the ones I'm going to hit. There are a few other more esoteric ones that have very minor performance impacts. For example, you can compile R. By default, R will compile as a shared library. So if you want to bundle R into other applications, this is possible. If you disable that at compile time, maybe it improves performance epsilon, but I don't care about this. If you want to know how to do that, you can see in the R installation and administration manual. But basically, we're going to talk about how you compile R, what compiler you use, R's bytecode compiler, and choice of blas library. Okay. So, using a different compiler. R was designed to work very well with the GNU compilers. Therefore, it works very well with Clang. Although you do need G-Fortran, which LLVM for some reason has no Fortran compiler. They're free. They'll compile anything. If you followed my instructions on the sheet and installed Xcode, you have Clang. If you installed R tools for Windows, you have something like GCC. You have the MinGW stuff. So R was designed inside of this. In fact, R is often called GNU R or GNU S. R is a dialect of the S language. So it very much lives inside of this ecosystem, works very well with GNU. That said, GNU compilers generally don't produce the fastest binaries. That's not really a controversial statement. I will say, for the moment, although this may change, don't bother with MSVC, the stuff from Microsoft. It just won't work. You can't compile R with the Microsoft compiler. Although Microsoft just bought Revolution Analytics, so maybe they'll change that. Who knows? Intel's ICC, and of course there are many other compilers. This is just an example. It's very fast on Intel hardware, and so if you were to compile R with ICC, you would get a non-trivial performance boost for everything you ran in R. How much would it be? Not a shocking amount. Probably no more than like 10%. I don't have hard timings to give you, but I have worked with them, and it is faster, but it's not going to blow your socks off. That said, it's free, right? So if you use a better compiler, better here means for your hardware, in a sense, then you'll get a faster R. So it is faster, but it's not entirely painless. Question?
So the Intel compiler I thought was cheap but not free.
Well, so you're referring to bullet 2 here, maybe. The Intel compiler is not free to use unless you can get like an evaluation usage of Intel compilers. If you do, my understanding is you're not allowed to tell anybody anything you discover. So if I compiled R with this evaluation, and I may misunderstand, please don't sue me, but you know, if I were to download that evaluation of the Intel compilers, and I were to, for example, compile R and say, here's what I discovered, then I could be in trouble. How expensive it is depends on your point of view and probably how good of a relationship you have with Intel. I'm not the person to talk to about that. I know if you just go to the website, it's at least several $1,000s, maybe more than that. I don't remember, and I'm not going to, I don't want to say something wrong. So the Intel compilers are, they're not free, and that said, if you have access to Exceed resources, you probably have access to Intel or Portland Group compilers or whatever. If you don't have access to an Exceed resource, it gets a little more, you may have to pay, right? Okay, so the improvements you get out of these compilers, for example, Intel, I'm just using this as an example. The improvements will be most visible on Intel hardware, sort of makes sense probably. Intel, one reason why I like plugging Intel is they actually have a dedicated page for how to compile R 3.0.1, I think, with Intel compilers. That's pretty cool. So if you do have access to Intel compilers, This will tell you exactly how to do it, and it's written by Intel. It's not written by somebody else. So it's pretty cool. Okay, so use a better compiler, R will be faster, and that's just a one-time, one-and-done kind of thing. And again, if you're on an Exceed resource, probably the R that you have access to has been compiled with one of these compilers anyway. So the bytecode compiler is a little different, right? Bytecode is sort of like, sort of like machine code for interpreters. I don't really know how to explain bytecode better than that, unfortunately. It'll make things a little bit faster, especially like maybe some lookups or something. But it was released in 2011. I believe Luke Tierney he's the lead author, maybe only author. I say it'll improve R code speed by 2 to 5% generally. So that's not 2 to 5% of the original runtime. That's 2 to 5% improvement. Not a lot. It's free. It is an improvement, but it's not fantastic. And it'll do best on loops. So by default, packages that you install may or may not be bytecode compiled. There are some caveats. The base and recommended packages, stuff like base and the utilities, stats package, these things that come with R, mass, these things are bytecode compiled. But if you're a developer of packages, by default it will not. You have to specify that when it is compiled, this package should always, or built, this package should always be compiled. So what are the downsides? Slightly larger install size for your package. Not a big deal today, because we're talking on the order of kilobytes. You probably won't notice. Much longer build process. So if you are developing your own packages, you probably don't want to bytecode compile until you're really, really ready to start testing performance or hand it off to other people. Because the difference in time can be extraordinary if you have a lot of R code. And again, it doesn't fix bad code. Back to this idea that R is dumb. R is not clever. It'll do what you tell it to do, right? So a real compiler, like a C compiler, will fix certain bad practices. Not all, but will fix certain bad practices. The bytecode compiler will not, and we can prove it. The upsides, it'll be slightly faster, and it's completely free. How does it work? You can compile any function you like explicitly in the following way. So you can say, we're just going to define this test function. We'll take single value x and add 1 to it. It's a very silly function, right? We're just going to add 1 to the function. So when I print it, this is what, when I say test, remember functions are first-class objects. So if I say test, enter, it's going to print the R-level source code for test. Looks like that. Now I can load the compiler, library compiler. It ships with R by default as of, when was it? Hang on. It was released in 2011. It ships by default as of like 2.13. We're way past that. But so you probably have it. I can compile my function, and I could actually even name a different object here, but I want to replace test with a bytecode compiled version of itself. To do that, I say cmpfun, so compile function, test. I'll replace test with it. Now I want to print it again, and we see some extra stuff, right? So it worked. We compiled it. And that's the bytecode. A bunch of nonsense, right? We can even disassemble it to see what that really means. And I look at this, and I know a few things about R, but I don't really know what that's doing. Again, it's sort of like machine code for interpreters. Whatever that's doing, it's actually different from what it would have done before. Okay? So simple to use, it's very straightforward. If you're installing a package, install.packages, you can set, so if you're installing from source, you can set the install options to byte compile in this way. From the shell, you can set R compile packages to 1 and compile that way. Or if you're a developer, in your description file of your package, you can say byte compile yes, and then it will byte compile. Also, I think lazy load yes will do the same thing. How much does it help, right? Here's an example that I cooked up to make it look good, and it doesn't look really maybe great. So we're going to define this function. For I and 1 to whatever the input n was, I'll take 2 times 3 plus 4, right? Remember, a real compiler I keep saying real compiler. A C compiler would basically just make that evaluation happen once, because I'm just doing the exact same thing n times. The bytecode compiler will not. So load compiler, I'm going to say f and then f compiled, cmp fun f. Load r benchmark. We're going to be using it for a while. Say n is, what is that, 100,000? And then benchmark f at n, f compiled at n, and we see they both take a really long time, right? However, the bytecode compile version is maybe 9% faster. That's great because it's free, but it's not the same thing as going like 100-fold speed up, which I will show you how to do in Module 3. But it is free, it's nice, but it's not going to solve all of your scalability problems. It's an important tool, but it's not the only tool. Okay. Here's another example. I don't even remember doing this. What does this do? Why is this here? Yeah. This is an example to show that for certain things, this was cooked up. This was designed to make the compiler look good. This is designed to make the compiler look bad. So if what you're doing is pretty far away from things like for loops, if it's functions that this is already byte-compiled, this is already byte-compiled, this is already byte-compiled, it's not going to help tremendously, right? And so here we can run this test, and you see it basically doesn't help at all, right? So that's basically the point of that. Okay, choice of your BLAS library. For Exceed folks, this is probably very routine, but outside of HPC centers, this maybe is not discussed as much as it could be. So the BLAS are these basic. Do we have any questions so far, by the way? Twitter? Okay. The BLAS are the basic linear algebra subprograms. They use the word subprograms to give you a hint of the date these things were made. And they were developed. Well, they're maintained. I don't know where they were developed. They're maintained basically down the hall from here, or one version of them. And so they include basic numeric matrix operations. So vector-vector operations, matrix-matrix multiplies, these kinds of things. The BLAS are used extensively in matrix factorizations. Why would any of this matter to you? Matrix factorizations are very important for statistics and data analysis. Principal components, linear regression, generalized linear modeling, all of it is matrix factorizations. All of that, okay? And then some is matrix factorizations. Or, you may have something dominated by matrix-matrix multiply. Even though you may be thinking about it in a different context, it still would be a matrix-matrix multiply. So the BLAS are sort of an ad hoc standard. They're a de facto standard is maybe the better way to say that. And there are different implementations. And some are drastically faster or slower than others. So here's an example. It's an example that I wanted you to be able to recreate on your computer. So I could say a lot more. This is just a simple example that you personally could recreate on your laptop computer. What are we doing? There's quite a bit of information to digest here. So we're going to have a matrix of some size, some square matrix. Here's an example, 2000 by 2000. And it's going to have random normal data. I'm going to look at the size of the object. How much memory is it consuming? You can use the object.size function in R to do that. And then I'm going to load our benchmark, and I'm going to compute x times x as matrices, and the singular value decomposition. We saw earlier that in principal components was dominated by singular value decomposition. So this is relevant real stuff. It's just a little bit abstracted. So what's going on here? This may even be difficult to read unless you have a version of the slides opened on your laptop. But I'm benchmarking the reference implementation, Atlas, which is a very popular implementation of the BLAS. OpenBLAS 1 means just one thread, one core. And then OpenBLAS 2, which means parallel on two cores, two threads. And we see that x times x on a 2000 by 2000 matrix, 2000 by 2000 matrix is about 31 megabytes of data. We can see the reference BLAS are the slowest by far. This is average wall clock time for 10 runs, so lower is better, right? So the reference BLAS are not doing very well. Atlas does better, but gets beaten by OpenBLAS. And OpenBLAS with 2 threads does better than OpenBLAS with 1. Same picture here, much more drastic picture here, same picture here, right? So if you build R without specifying, and if you're like on like an ordinary Debian system and you're installing through the package manager, some things I'm about to say are not true, you knew that. But for most users, if you go to the R website and download R, I believe it is still the case, my understanding is it is still the case, you're getting shipped the reference BLAS, the slow ones, right? So how can you use a different one? You can find out in the R installation and administration manual. There's another thing I didn't plug here. Revolution Analytics has this thing called Revolution R Open. It is one of the versions of R compiled with, I believe, Intel compilers and shipped with MKL. MKL probably would be faster than the OpenBLAS one here. Okay, so it's very, very, very fast on Intel hardware. If you're not on Intel hardware, I don't know how it'll do, but it's very, very, very fast. And they give it to you for free. So it's called Revolution R Open. Now, again, I'll plug the fact that if you're on Exceed resources, we have things like MKL, ACML. There's 100 of these different BLAS implementations. And the people building R to use on that system probably set it up to use a good BLAS implementation. But for users outside of Exceed, desktop users, you can still get good improvements. All of these are free, by the way. The reference BLAS are free. You don't want them, maybe. Atlas is free. OpenBLAS is free. In fact, they're Libre. They're open source. The parallel BLAS doesn't always play nice with the parallel package. They may have fixed that. I've had a much harder time trying to break it recently. There was a time where it was very easy to break it. But they've been working on it. But parallel package we will talk about in Module 4, the last 45 minutes. But something important to bring up. So, if you compile R itself with a different C and Fortran compiler, you will get better performance. The compiler package, the bytecode compiler, offers very, very small but free speedup. And as I say, it works best on loops. There's also the BLAS. Okay? Any questions about that before we get to improving performance of R code? Okay. So I can't do a proper poll for all the folks remotely, but here, if I could get a show of hands, how many have been working with R? If you would just indulge me. You've been, almost everybody. That's great. Okay. So you may know a lot of what I'm about to say, but I hope I can give you some interesting new perspectives on it. If you have not been working with R, which may be true for many of the remote folks, for example, service providers who are interested in servicing R customers, they, I suspect, will have a very interesting few minutes here. So R has for loop, while loop, has no gotos or do whiles, and they're very slow. You generally want to avoid them at all costs. Okay? The best practices for loops, you want a profile, most try to avoid. Of course, evaluate the practicality of a rewrite to something else, and we're going to talk about all of these things. And always preallocate. What do I mean by preallocate? Here are 2 examples. I'm using the word no init for not preallocate, with init for with preallocate, sort of shorthand. These 2 do the exact same thing. One does it in a very bad way, right? What's happening? What we're going to do is we're going to take input in, right? So some integer, let's say 10, and then for I in 1 to 10, we're going to store the square of I. So I'm squaring all numbers up to n and returning them. Very simple function, right? Here, my return is going to be called x, and here I initialize it as just an empty vector. Each iteration, I compute the square, and then I update x to include the new value, right? I forget what people call this, pushback or whatever. But so each iteration, I'm growing the size of x, right? It started out with no elements. By the end, it's going to have n of them. Here, I start with n of them, and I fill as I go, right? The only difference. But there's a reasonably big difference in performance. And the larger you make n, here it's actually fairly small, 1,000. The larger you make n, the more pronounced this difference will actually become. Why? It actually has to do with memory operations, cache misses. You can actually look very closely at what's going on with PBD-PAPI. But the basic idea is each iteration of this loop here, the R interpreter is going to take the values for x, the value of the new value, or the new square value that we've computed. It's going to allocate a new vector, length 1 larger than the original. It's going to fill that vector with all the old values of x, and then add the new one, and then throw away the old value of x, each iteration. And so the larger n is, the more pronounced the performance difference here is going to be, because we have more and more and more unnecessary memory operations. And this may all be trivial and obvious to you, but this is something I see in the wild all the time. It's a very important thing to understand and to avoid. A simple way to avoid that is to use Pli functions. Just avoid for loops altogether. So the Pli functions are functions that apply functions to data, right? It's basically loop sugar, as I say, although some of them are slightly more, slightly less. So we have apply. Apply takes a function, applies it over the rows or columns. They call them margins, the rows or columns of a matrix. Lapply applies function over a list vector. Mapply over multiple list vectors. Sapply is basically a cleaned up lapply if it's a proper vector, not a list. Some other mostly irrelevant ones, tapply, vapply, they mostly don't get used. R also has a map and a reduce. They are map reduce that you've heard of. How do they work? So here's apply. Have a matrix, our old friend, 1 to 10 with 2 rows, right? If I say apply, the data is x, this matrix. The margin is 1, and this is just some strange R nonsense. That means do it to rows. And then the function is sum. What am I doing? What is the output here? Exactly right. It's going to sum across the row. First value is 25. Sum across this row. Second value is 30, right? So it allows us to avoid a loop. I will point out, apply, if you look at the source code, is actually nothing but an ordinary R-level for loop. So it's nice, but it's nice as a form of sugar, syntactical sugar, but it's probably not particularly performant. Here's another example. Now the margin is 2. This means across columns, what are we getting? The column sums, right? And you can also do across margins 1 to 2. This is very rare, and I think it's actually kind of silly, but you could do it. And so it's going to apply the function basically element-wise. I think there's maybe a better way to do that, but whatever. You can. So lapply. What does lapply do? Lapply says, given a list, apply the function square root to this data here, 1 to 4. And so the output is a list containing the square root of all of those elements. Pretty simple stuff, right? Sapply is the prettier version of lapply if you're dealing with vectors. So if I say sapply, it's going to return a vector. This is the same thing as calling simplify to array on lapply, but is just a shorthand. But just notice, we're taking this input set and we're applying a function to it. I'm not really prepared to call this vectorized. A lot of people call this vectorization. I disagree, and we'll talk about vectorization in just a moment. More than maybe you ever thought you wanted to hear about vectorization. But I'm not fully prepared to call this vectorized. Why? Lapply and sapply are doing some special things. They're not just for loops. They're doing some special things to avoid interpreter overhead. But they don't avoid that much interpreter overhead. They're still operating, each evaluation is still operating at the R level. So you're still working on this function, which could be some dumb function. Vectorization, I think, should be more ad hoc. So transforming loops into plies. Here's an example. We have this. We initialize our vector, and then we're going to apply my function at the index I and store it in the vector. This just becomes s apply 1 to n my function. So, you know, if you've been working with C++ 11, it's full of this kind of stuff. This functional programming stuff is very useful abstraction, but it may actually improve performance. It may degrade performance, as we'll see. Best practices. They're basically shorthand for loops, syntactically, but semantically, they're actually a little different. They may not be much faster if you're using the bytecode compiler. You know, that sort of narrows the gap between the performance of the loop and the ply. But there are good reasons why you would want to think in these terms. It basically gives you free task-level parallelism, as we'll see in section 4. You can do between plies and lambdas. A lambda is just sort of like an inline function expression. Between plies and lambdas, you can do some really, really crafty things. But you know, you shouldn't lose your mind and do something crazy that no human can parse, right? This is a silly example I cooked up for demonstration purposes, but you know, so like cat s apply and then a lambda. Inside the lambda we're s applying, a lambda inside that lambda we're s applying, a lambda inside. It's very difficult to process what this is doing. If you know what this is doing, I'd actually be very impressed. But things like this are incredibly hard to debug. And you see people do crazy things like this. I don't recommend it. You can maybe make this look a little better with that. You're supposed to pronounce this with an extraordinary French accent. Those are the rules from the package author. The package is called MAGRITTR. I don't know. In my southern ways, I might say Magritter, but Magritter, I don't know. Those are his rules. There's this package everybody knows about, right? You can maybe make this. You can debatably make this look a little nicer with that package. I still think you're getting yourself into a lot of trouble for debugging and especially profiling. So I don't recommend you go crazy with this kind of stuff. But they're very useful. That's the point of that. So vectorization. Yep, sure.
Can I ask you a question?
Yeah, sure. Sure.
All right, just so that everybody can hear it, so Drew doesn't have to repeat the question. I have a question that says, what about using PLI functions from the PLYR library?
Oh, Plier, yeah.
Those are faster than apply and lapply, to which someone did respond, not in my experience. So if you could give us some thoughts on that, we'd much appreciate it.
It's a great question. So the question is about Plier, and it wasn't asked, but there's also dplyr, right? I have a lot of thoughts about Plier and dplyr. So Plier, in my experience, has been aggressively slow. You should only use Plier, in my opinion, you should only use Plier if performance is basically irrelevant. It offers some extra nice abstractions. So all of these ply functions are just abstractions of different kinds of loops. Plier offers additional abstractions. The performance tends to be pretty crummy. There's, I don't know if I would call it a rewrite. There's a new thing now called dplyr. Dplyr performs much better, but it doesn't exactly do the same things Plier did. It has a very different point of view about the world. My opinion is, there's also the other issue that doesn't get brought up often, which is portability, right? These are shipped with R, right? Extra packages, you should always think in the back of your mind, you know, who's maintaining it? Is it going to be around in 10 years? Probably with Plier and dplyr. But, so to answer a question that was not asked, dplyr, I think, is doing a much better job of trying to make higher-level expressions performant. My understanding is Hadley basically gave up on Plier. I don't think it gets updated. I could be wrong. I think the performance of Plier is crummy. So it's a great question, and I don't want to badmouth it, but I personally don't enjoy it. Is that fair? Right. So, okay. So vectorization. Let's talk about vectorization. So vectorization, if I have, let's say, vectors, x and y, I can say x plus y. I don't have to write a loop for I and 1 to the length of x, you know, store, preallocate, store x plus, you know, it's just going to form that sum as a vector or whatever, right? If I say x, comma 1, so we're imagining x as maybe a matrix or a data frame. Then comma 1 means I'm just looking at the first column. I'm going to set every value to 0. That's a vectorized operation. If I say R norm of 1,000, I'm going to get 1,000 random normal values back. That's a vectorized operation. So if you've worked with another high-level language like MATLAB or Python or Julia, although Julia has sort of an interesting different perspective on vectorization as I understand it. Julia is a very neat language. I encourage you to look at it. But you know, if you've used MATLAB or Python, you know what vectorization is. And you basically want to use these, I'm choosing my words very carefully, pre-existing compiled kernels to avoid interpreter overhead. So they tend to be much faster than loops implies. I challenge you to find an example where that's not the case, actually. Although vectorization can use a lot of memory, it can really gobble up your memory. So here's just a simple example where we're going to, you know, I want to call R norm on one value 1,000 times versus calling R norm on 1,000. The difference is staggering, right? So you should always use the fact that this is vectorized. R norm expects you to hand it one value, say 10, and you get 10 back. You don't have to call it 10 times, right? Vectorize if at all possible, if we're in this frame of mind. But again, this can really gobble up memory. Putting it all together, right? How does this stuff relate to each other? Loops are slow. Apply and reduce are actually just R-level for loops. They're just very simple sugar. All of these things are not. There's something a little different. And they're sort of craftily trying to avoid some extra interpreter overhead. Ply, and when I say ply, I mean the ones labeled here. I don't believe it's fair to say that those are vectorized. I really don't think that's reasonable. Vectorization is very fast, but it needs a lot of memory. How would you do better than vectorization? You would interface to a compiled language, which is what we will talk about in the next section. So here's a very simple example, and then I believe we'll finish up for a break in exercises. So if we want to compute the square of the numbers 1 to, what is that, 100,000? We can do this with a for loop without preallocation, for loop with preallocation, sapply, and vectorization. Okay? And we can see what's going to perform the best. You probably could guess, right? We've already seen these two. These were the first two examples we looked at, remember? So I'm only going to define these two new ones, and they're very simple. So the square sapply function is just going to say sapply 1 to n. I'm just going to define a lambda here. So an inline function that takes argument I and squares it. Right? Pretty simple. For vectorization, so this is interesting. I chose to say 1 to n times 1 to n. I could have said 1 to n squared, which would have been more consistent. This will actually, so like, if you say 2 times 2 in R, that's actually going to be faster than 2 squared in R for strange reasons. And that's true in like compiled code too, but it tends to be more surprising, I think, in a language like R, to folks who are using a language like R. So maybe this is even slightly unfair, but not that unfair. If I change this to a square, it wouldn't change the performance that much, right? It's not gonna really change the picture here. What is the picture here? If you do a loop without initialization, it's really bad compared to vectorization, right? It's really, really bad. 2,400 times slower. And if you grow in, it'll be even slower still. With initialization is much better. It's merely 133 times slower than vectorization. The sapply, notice, did not actually perform that well relative to the for loop. So sometimes for loops actually will beat plies, especially on very simple kinds of things like this. If it had actually been a more complicated function with a smaller n, the ply may have done better. Or if you really make n really big, then maybe the ply would win. In general, it's kind of hard to predict, in my opinion. It's kind of hard to predict when one will overtake the other. That said, I will reiterate, thinking in terms of plies can be very beneficial because it gives you completely free task-level parallelism. I will show this in the last section. So quick summary. Preallocate your data if you're going to use loops. Vectorize when you can't. and try apply function, vectorize as often as you can. Try apply function whenever you can't. And the next best thing to vectorization is to basically make your own vectorized function, is to make your own compiled kernel, which is what we are going to talk about next. But for now, go ahead and we're going to have a 30-minute break. So this is 15 minutes for exercises plus 15 minutes of just go wild. Then we'll return here for, I think, maybe the most important thing that I will be talking about today, which is interfacing to compiled code. This is something that always sounds really scary to people. It's really crazy easy in R. And I really hope to make that point very clear when we return to it in about 30 minutes. So if you have questions, feel free to ask them. Take a look through the exercises.